So yeah, today I will review this paper called Suppressing Quantum Errors by Scaling a Surface Code Logical Qubit. So this paper was published on February 22nd, 2023, which is quite recent by Google Quantum AI. So why is this paper worth reviewing? So Google Quantum AI has proposed their roadmap towards the large-scale fault-tolerant quantum computer, and there are 6 milestones related to it. So the first milestone was to show that there's some quantum supremacy that we can achieve, and that was shown by the paper that was published in 2019. And this time, they have published another paper, which is this one, and they argued that they have achieved their second milestone, which is about logical qubit prototype. So what is a logical qubit prototype? So qubits are inherently susceptible to noise. So the first quantum error correction method has been proposed by Shor in 1995. And there has been different error correcting methods has been also proposed. So one of the method was is called the surface code, and it was proposed by Kitaev in 2003. And in this paper, the Google Quantum AI people are focused on surface code to show that they can actually make scalable error correcting code. So theoretically, as the quantum error correction relies on the fact that relies on encoding a qubit of information in collection of physical qubits. So theoretically speaking, if there are more physical qubits involved in quantum error correction, that means the error suppression rate would be better in theory. But however, in practice, when there are more physical qubits involved in the error correction, there are more actually those physical qubits are vulnerable to noises as well. So in practice, as the system size of the error correcting code becomes larger, the error correction scheme actually does not work. But in this paper, these Google people show that this surface code scheme can be actually scalable. So I will just share the conclusion first. So the authors experimented distance 5 surface code and distance 3 surface code on a Sycamore device, which is also a superconducting system with 72 qubits and 121 couplers. So you can see the surface code on figure A right here. So the yellow circles represents the data qubit and the blue circles represents the measurement qubit. And this red line represents the surface code of a distance 3 surface code. And the rest colored components represent distance 5 surface code. So in this Sycamore device with 72 qubits, you can actually configure either one distance 5 surface code or 4 distance 3 surface code with different qubits. And actually in this presentation, I will not go into the technical details of the surface code because I believe one of the other presenter actually presented surface code on in other presentation. And the figure B represents the result from experimenting with distance 5 and distance 3 surface code. So the red line represents the logical error probability of distance 3 surface code on each error correction cycle. And the blue line represents the error probability of distance 5 surface code. We can see that the error probability of distance 5 code is slightly better than distance 3 code. And Google Quantum AI actually claims that even though this is only a marginal improvement, this is like a stepping stone towards the fault tolerant quantum computing. And yeah, they argue that the surface code is actually scalable. So if we go into a bit of detail, the authors first presented the error detection probability of two surface codes. So the figure B and C represents the detection probability of distance 5 code, and figure D and E on the right represents the detection probability of distance 3 code. So here you can actually see that there are like weight 4 and weight 2, and this means that actually in the surface codes there are two types of measurement qubit. The square ones represents the weight 4 measurement qubit because it is connected to 4 adjacent data qubit, and this other types of measurement qubit, which is like a half circle kind of measurement qubit, is connected to 2 different data qubits. So this is a weight 2 measurement qubit. And we can see that weight 4 measurement qubits detection probabilities actually higher than that of weight 2 measurement qubit. And that is quite natural because it's connected to 4 different data qubits. And the actual value were like 0.185 and 0.119 for 2 different types of measurement qubit in distance 5 code. And for distance 3 code, the values were 0.175 and 0.115. And the last graph down here is the simulated result. And the simulated result of a distance 5 code, and the values were 0.18 and 0.116. What we need to take from these plots is that the relative consistency between code distances suggests that the system size does not actually change or affect the component error rates, like the error rates of different sources. Yeah, and just to note that the detection rate at the very beginning is almost 0 because there is no syndrome measurement ahead. So there's like no detection error to detect or compare, or I mean no parity to like compare from the previous result. And at the end of the cycle, also the detection probability is very low because in their experiment setting, at the end of the cycle, they actually measure the parity of the data qubit rather than the measurement qubit or the stabilizer. So the actual detection probability is lower. And after detecting the problem, like the whole point of error correction, detecting the problem is to decode the error and fix the error. So here's the result here's the result of a logical error probability. So with the errors detected, they actually express the physical error events as a hypergraph where each detectors are vertices and errors as hyperedges with a probability. And they use 2 different decoders, belief matching and maximum likelihood decoder, to actually decode the error events. So the figures on the left there are actually the results from the maximum likelihood decoder. So the first plot is just the same plot that I showed in the previous slide. And the second plot is the fitted plot, plot from the figure A. We can see that in the second plot, the logical error probability per cycle is about 2.914 for distance 5 code and 3.28 for distance 3 code. So there were like 4% improvement with the distance 5 code. And yeah, with this result, we can see that distance 5 code actually works better than distance 3 code, even though only slightly. And the figure C shows how each distance, how each code improves as we improve the actual physical error of the device. So which means that these Google quantum AI people actually optimize their device so that each component, like single qubit rotation or 2 qubit gates, have less or higher fidelity or higher accuracy. So the improvement, so the data point was taken from this left bottom to top right. We can see that when there are more physical error, actually the distance 3 code works better. But as they optimize their device, the improvement in distance 5 was much faster than the distance 3 code. So the red line here represents that the distance 3 code and distance 5 code works the same. But we can see that the distance 5 code improves faster as the device was more optimized. Yeah. And here is a bit more on the errors. So the figure A represents what type of error are prevailing in the current device. So in order to get the first plot, they simulated the distance 5 code with the varying physical error rates. And they were able to notice that the CZ gate errors and the dynamic decoupling error are prevalent in the current device. And figure B shows what error will prevail if the error correcting system becomes larger. So in order to experiment this, they use the distance 25 repetition code, which is more like a 1D array, whereas surface code is like a 2D error correcting code. So with the repetition code, they can only fix the bit flip error, not the phase flip error, but they can actually make the error correcting system bigger and also achieve a lower logical error probability. So that here we can see that with the 25 repetition code, they were able to achieve around 10 to the like negative fifth something like logical error probability, but in the end it kind of saturates. And the reason why it saturates is that when the system becomes larger, there are different error sources coming into play, which are like high energy impact on the system. So one of such event would be something like cosmic ray affecting the superconducting system, and this is and that affects the like the measurement process or other process, so that there are like spikes in the detection event count. So the authors actually removed these effects, and they were able to see that after removing the high energy event, the logical error rate was much smaller, or like going lower. Yeah, so the point is that when the system becomes larger, the current prevailing error factors would not be significant anymore, but there would be like other error sources coming into play. And this figure C represents it's like a simulation of the logical error performance of surface codes ranging from distance 3 to 25. So basically there are 3 regions. The first region is this red region where the the error rate of the larger system is bigger than the error rate of the smaller error correcting code. And this blue region is where the error rate of the larger error correcting code is actually smaller than the error rate of the smaller error correcting code. So this blue region is where we need to achieve where we want to arrive in the end. And these authors claim that they're currently at this like a yellow or orange kind of region where the error probability, logical error probability, actually improves as when up to like a certain certain size of error correcting code. Like, but if we make the code bigger, then the performance would actually degrade. So yeah, that is the current situation for them right now. And yes, and so the summary is that even though it's only minor evidence, there's like a experimental evidence that the surface code is scalable, and increasing the code size does not actually affect detection probability significantly. And also they showed that the distance 5 code improves faster than distance 3 code with the current device setting. And currently errors from a control Z gate or dynamic decoupling are dominant, but if the system becomes larger, highly correlated errors such as cosmic ray impact will dominate. So the whole point is that we still need a lower physical error rate in order to make the surface code scalable. Yeah, so that was the end of the presentation, and yeah, I'll take any questions if there's any. Yeah.
What's dynamic decoupling?
Oh, to be honest, I'm not really sure what dynamic decoupling is, but as far as I know, it's like at the end of the computation, like there's like a measurement process, and I read there's like some qubits becomes like idle rather than like affected by any operation or measurement process, and that's like when dynamic decoupling happens. Yeah.
So you mean that the qubit is not operated by some operations and qubit.
Right. So I guess like it just like decoheres like because it's like not like getting or yeah, it's not working anything. So yeah. Yeah.
Confusing the meaning of the word scalable.
Okay.
Is the meaning that the code given by certain code can produce reliable results?
Yeah, so by scalable means so until now it was experimentally not possible to actually make a larger or bigger error correcting code. So what I meant by scalable is that yeah, if we actually have a lower physical error rate, then the larger error correcting code would be available. Does that make sense?
The error rate is low.
Yeah, right.
And we need large error correcting code.
Yeah, because if we have larger error correcting code, theoretically we will have a lower errors. We will have a higher error suppression, which means like lower error rate. Yes, but that is not currently possible because like physical error on qubit is like way too high to implement a large error correcting code. Does that make sense?
Yes.
Yeah. Okay.
So I guess scalable means you can suppress to some bound using lots of qubits.
Oh, yeah, simply speaking, yeah, that's correct. Yeah. Yeah.
How far are we? So like, what's the error rate of the?
So those in this paper, they suggest that they need at least like 20% improvement with the current error rate in order to like get closer to this greener region. But if you want to like actually make a really large like fault tolerant quantum computer, you need like much better physical error rate, like much lower physical error rate. That's what they are stating in this paper. Yeah.
If my understanding is correct, I think there are two issues, three code different algorithm code and five different algorithm code.
Mm-hmm.
And we cannot use the code different because of the physical error rate rules. Am I right?
So the physical error rate is fixed, but if more like physical qubits are involved in the error correcting code, then the error suppression will not happen because So
their conclusion is that we cannot
So I guess their conclusion right now is that if the error correcting code becomes bigger than distance 5, then probably the error suppression will not happen. So it's
negative measure. Am I right?
Yeah, it's like negative but positive at the same time, I guess. Yeah. Because until now, even like their result was not even possible until now. Yeah. Yeah.
Here, did they show it only on Sycamore's Google Sycamore processor, or like it works for any superconductor?
I guess this only works on their device right now, because they also chose the surface code because it was more like suitable for their architecture.
Yeah, I was curious, like, if you compared it with IBM, like even though they have the same superconducting, but like Sycamore has some of these couplers, right? So will that have any effect in the scalability? Did they kind of show this kind of?
Yeah, I think they chose the surface code because surface code requires like each data qubit and measurement qubit to be connected to four adjacent qubit, right? So Sycamore supports that, but like for example, IBM's device does not have such architecture. So yeah, if they experimented the same thing on IBM Q device, then the result would be worse. Yeah.
Can you explain specifically in which part they made this conclusion? That made them to conclude that increasing the scalability with data.
I guess this figure is their like main result. So yeah, this figure basically shows that the logical error probability of distance 5 code is lower than distance 3 code. Yeah, so the blue line is the distance 5 code and red one is the distance 3 code. So
what is the x-axis?
x-axis is the cycle, like QEC cycle after each cycle.
Thank you.
In the slide, so epsilon d is logical error rate corrected by d distance surface code, right?
Yes, yeah.
And why is it fixed?
In
the figure.
Which figure?
In that figure.
Oh, in this one?
Yeah.
So in this figure, I guess they're basically
Oh, sorry. What's the error model scale factor S?
so the error model scale factor is basically like, so what I understood that is that if this is the value S is smaller, then it's better because the error model is like it does not scale even if you increase the code size.
And I mean, isn't there like a definition of S in the page? I feel like it's the number that you take.
Error model scale factor. Yeah, I don't think they specifically mentioned the definition of this S. Yeah, it's not, maybe it's in the supplementary document, which is like 50 page or something. But yeah, I didn't go through that one, so yeah, I'm not really sure. Yeah.
High energy event.
So the high energy event is something like I just like also read this from just like an article, so I'm not really like very well knowledgeable about this, but you know, like something like cosmic array can affect like superconducting devices. So it disturbs the system and it creates like errors, like you know, like other sources of errors. So what they're saying is that when the system becomes larger, uh yeah, errors like cosmic area or cosmic ray or other high energy event would like affect the system. And yeah, so they're saying is that if the system becomes larger, we rather need to focus on those type of errors rather than the types of errors that we are focusing right now.
Is the cosmic error hard to detect in general?
Detect? Oh, they didn't mention that in detail, but they said they were running like several experiments, and in one of the experiment they were like able to detect this some sort of like spikes in their measurement. So they consider that as the high energy impact error, and they like remove such error to yeah get this result. So yeah, I'm not sure how often that such event happens in real life.
So that's the actual measure experiment data. Figure.
Yeah, I believe this is the experimental data, which seems very smooth. Yeah.
And thank you for the presentation.